So Tuesday lab next week. If you absolutely need, like if you run out of time this week, there is Tuesday lab next week. Still technically a lab there. So if you do not finish, it's your last chance for general unknown. That's for Tuesday, Thursday, or Friday lab. But hopefully most people finish this week. All right, electrochemical cells. So in our electrochemical cells, we have an anode, we have a cathode. And in an electrochemical cell, it starts at the anode, the electrons are lost there, they travel through the load, they go to the cathode. So anode is always oxidation, cathode is always reduction for a voltaic cell. And in chemistry, the anode is more negatively charged. And so anions are negative and the electrons are repelled away from the anode. They are attracted to the cathode. And this kind of works with the standard cell potentials. So we're going back here a little bit just to review. Also do need a salt bridge between the two, because if you just hook these things up, what's happening is you're creating ions in these cells as the reaction is running, or you're using up ions in one of those cells as the reaction is running. And so you'll end up with a charge imbalance. The salt bridge lets or at least some of the anions or cations flow back and forth to balance that charge. If you don't do that, then the cell just stops working. So you should know for the final how to draw this, at least very roughly, right? Like a bucket for each beaker, some sort of electrode in those things, a wire connecting them to some load like a light bulb, the salt bridge in the middle, and be able to label those. Talked very briefly about electrochemical cell notation. Not super important, but it does tell us how to write out a cell without having to draw out the entire picture. And it separates different phases, oxidation and reduction, but also solids from things that are aqueous. But you can have cells that have almost everything in the aqueous phase. It's like for this reaction, the permanganate, the hydrogen, and the manganese all are in the aqueous phase, and the electrode there is just a platinum electrode. Something inert, something that's not reacting. It's just there to conduct electricity through the solution. So I just label it as platinum. So this chapter ties into, and we're going to we do completely bring this back to Gibbs free energy by the end of this week. But again, one of the big goals here is how do we predict which of these electrochemical reactions will be spontaneous? Which ones are going to happen on their own? And so for Gibbs free energy, that was like how we determined if a reaction was going to be spontaneous, because it takes into account everything, including, well, actually, let me ask you guys, what makes a reaction spontaneous? Huh? Rounded? Surroundings. What about the surroundings? Huh? Temperature of the surroundings plays a part in it. But what always happens? Yeah, let me rephrase the question. What always happens for spontaneous reactions? They don't require extra energy. Why? You go from higher to lower energy, yes. Huh? G is negative, yes. So G, calculate it. But the big thing that G takes into account is the second law of thermodynamics, having to do with the entire universe. Entropy increases. The entropy of the universe always increases. So the entropy of the universe, which was S It equals the change in entropy of the system plus the change in entropy of the surroundings. Now, entropy is kind of a hard thing to calculate directly. So instead, we can use things like heat and the temperature of the surroundings to determine if my reaction affects the surroundings enough to increase the entropy of the surroundings, or if it decreases the entropy of the surroundings. Or does the entropy of my system change? And so really we ended up taking this and we said, well, the temperature, or the system, delta S the system, plus really our surroundings are going to be affected by our system. How much are they going to be affected by our system? What's the change in heat or enthalpy divided by that temperature? And that'll equal delta S for the universe. And eventually we boil this all down to delta G equals delta H minus T delta S, all for the system. So this equation is really a specific derivation of this increasing the entropy of the entire universe. It's just simplified so that we can think about it in terms of just my one reaction. I don't need to think about the entire universe necessarily. I just need to think about my reaction and its surroundings. And so we can use that really simple equation to make predictions about whether or not reactions are going to be spontaneous. And a big part of that is, and as somebody said, energy is decreasing. Right? We're going from high energy to low energy. The same thing applies to electrochemical reactions. But in electrochemical reactions, we're talking about whether or not things are going to be spontaneous or not in terms of the voltage that they produce in a spontaneous direction, or as we write them from left to right, or if it'll be spontaneous in the reverse direction from right to left. So these cell potentials at standard conditions, remember the little zero means standard, is going to depend on the two half cells that I have, the two half reactions that we put together. And so we covered this last time, and we are going to be talking about energy flowing from high potential energy to low potential energy, but that's difficult to see. And it's actually kind of difficult to quantify. So one of the things that we did is we said, or that we did, that chemists did, is that they said, well, let's just, if the only thing that really matters is the difference, remember a lot of these things are state functions, it just matters where I start and where I end, whether it's high to low or low to high, then if I just set something as my standard and I compare everything to that standard, and I can say, how do those compare to the standard? And then I can compare them to each other based on how they compare to that standard. So we set a benchmark. We say, this is 0, compare everything to that. And for electrochemical reactions, that's the standard hydrogen electrode because it's easy. So we have a platinum electrode with hydrochloric acid, which gives us the H+ ions. That's really the important part of this. The chlorine doesn't really matter, at least in this class. And then the hydrogen gas is what's being produced. And so when we have this half cell, we set its half cell for the cathode as 0. And because the half cell for the cathode is 0, then the half cell for the anode will also be 0. This is our baseline. Everything is compared to this. And so we can take our hydrogen half cell and connect it to a nickel half cell and a zinc half cell and a nitric acid half cell and compare how those voltages or the voltage of each changes. And the convention is to do that in terms of reduction potentials. Could be oxidation potentials, but we do it in terms of reduction potentials. So if we hook up like a nitric acid solution, which really it's the nitrate here that's reacting. So I've got nitrate in a solution and I hook it up to my standard hydrogen electrode, then I can read as a load some voltage from one to the other. And when we do that with, zinc. Why did I say nitric acid? Zinc, I was looking at the nitrate ions. The zinc, will oxidize spontaneously, which I just wrote the plus in there, but there's a, right, it's positive 0.76 volts, which means that electrons are moving from the anode to the cathode from left to right, which is just because we draw it that way. Which means that the voltage of zinc compared to my standard hydrogen electrode is positive 0.76 volts when it's the anode, when it's being oxidized. And then that flips, because it's the oxidation potential, but we write them all out in the table as reduction potentials. And so we're comparing this to hydrogen. And since that's positive, that means that the electrons from that zinc would rather not be in that zinc. The electrons in the zinc are in a higher energy state. When they move to the hydrogen, they move to a lower energy state, so the reaction is spontaneous. The overall voltage is positive, but the way that we write out the cell, like the half cell potential, here is the anode, is that this is negative 0.76 volts. And you can kind of think of that negative 0.76 volts is it wants to push electrons away with 0.76 volts, at least relative to hydrogen, because everything's relative to hydrogen. So a more negative cell potential, half cell potential, because it's for the oxidation, means that it wants to lose electrons more. It wants to push those electrons away. The more negative it is, the more it wants to get rid of its electrons. And the more negative it is, also the greater the potential energy of an electron at that electrode. So an electron at the zinc has a greater potential energy than an electron at the hydrogen. If we take copper, though, and we hook copper up to this standard hydrogen electrode, we get a voltage of positive 0.34 volts, which means that the reduction potential, I should write this on here, this is the reduction potential of the copper is negative 0.34 volts. So compared to the zinc, so zinc E cell is negative 0.76 volts. Copper is negative 0.34 volts. Which electron has higher potential energy? Is it a higher potential energy at the zinc or at the copper? Which one is pushing its electrons away more strongly? Yeah, the zinc. The higher the more negative the electrode potential, the more strongly it wants to push those electrons away. And the higher energy those electrons are when they're at that cell. So zinc is pushing its electrons away with negative or with 0.76 volts. Copper is pushing them away with 0.34 volts. So if we hooked up these two cells, if we connect the copper, zinc and copper, just to make this a super rough, are those going to move from the zinc to the copper, or are they going to move from the copper to the zinc? Well, the electrons. Which way will the electrons go? From the zinc to the copper? from the zinc to the copper. The zinc has the more negative potential, so it's pushing those electrons away more strongly. So we would expect this voltage to be positive going from zinc to copper. It would be negative going from copper to zinc, because we'd be forcing them, in a sense, in the opposite direction from a lower potential energy to a higher potential energy. Okay. Right, which is what we did here. Oh, because the E cell is negative, then this is positive. Well, then it's even more, because if the E cell for the copper is positive 0.34 volts, that means that it's pulling electrons toward it. And the zinc is negative, so it's pushing them away. Had that backwards from the first one. We're going to skip that because I'm not going to give you two different ways to do it. If you want to talk about, there's another way to think about these, but let me know if you want to see that. It kind of makes more sense to me, but so these are the reduction potentials. This is like the table of like standard potentials. They're all written as reductions. So everything here is gaining electrons from left to right, which means though that you can just reverse this and they're all oxidations. Right? So we had to pick one or the other. We picked reductions. I'm sure there's more reason than just flipping a coin and picking one, but this is how you'll see them written out. So they're all written as reduction, half reactions. And again, we can think about these as being all relative to hydrogen, not just think about them as, but they're all relative to hydrogen. So if you connect all of these to a hydrogen cell, the electrons will be either moving towards the hydrogen cell or away from the hydrogen cell. And so you get positive voltages when they're moving towards it. So everything above hydrogen, these are all moving, well, I should say moving to the H plus cell. These electrons would all spontaneously move away from the H plus cell. And so we get negative voltages. So since we set this as 0, we compare everything to that, and then because we have these relative voltages, we can compare the relative voltages to each other. See what's the difference in potential energy between those. So anything greater, with a greater tendency towards reduction, is positive relative to our standard hydrogen electrode, which means again, as written, the electrons will move away from that greater positive to hydrogen. If they're negative, then they're moving in the opposite direction, which does also apply to all reactions. The sign just tells you which way the electrons are flowing. Okay. So if we want to use these, there's a couple different ways that we can use this table. We can use it quantitatively, and we can say, what is the voltage of any cell going to be? So if I take this reaction, I've got lead and I've got chromium reacting. And so to figure out which of these is going to be, or I guess what the standard electrode potentials or the standard cell potential is going to be, I need to find the voltage of each of these half reactions. So one of my half reactions will be lead, and the other half reaction will be chromium. And the thing that you'll notice when you start looking at this table of all of these reduction potentials is there's a lot of different oxidation states. And so I think chromium in particular So chromium's down here. Sorry, it's a little blurry. All right, so I've got chromium 3 plus going to chromium 2 plus, and I've got chromium 3 plus going to chromium solid. And those are going to have two different potentials. So you got to make sure that you're picking the right one. And for this one, it's the complete reduction of chromium. Or actually, I guess in this case, it's the oxidation of chromium. And then we also need lead. Lead, fortunately, only has the one here. So negative 0.13. And then if we go back to our reaction, right, what's being reduced? Yeah, reduction is gain. So this is being reduced. Then chromium is being oxidized. The way that you can just memorize this is it's always cathode minus anode. But you got to know which one's the cathode and which one's the anode. So which one's the cathode? Yeah. Honestly, the anode's easier for me to find because I always think of starts at the anode, electrons are lost there, oxidation is loss. So whatever's being oxidized is the anode. So chromium here would be the anode, and lead is the cathode. Cathode, anode. So because lead's being reduced, that's the cathode, that potential is exactly the one from this table, which is going from left to right, because that's the reduction of lead. So negative 0.13. And then it's always minus the anode, which for chromium here is negative 0.73. Negative 0.73. I'd really encourage you to write these like I have here, where you do, it's cathode minus anode, but like put your anode in parentheses. So you don't forget that the sign of the anode needs to go in those parentheses because the minus is part of the equation. So if it's minus a negative, then yes, you're adding. Actually, I don't need to do this one in my head. I did this earlier. So this is a positive, right? Because minus a negative, 0.60 volts, which is my E cell, standard cell potential. And this is, it's not a tricky question, but this is the kind of thing that, like, if you really want to understand why it is this way, then asking the question, why is there a negative in this equation? Why is it cathode minus anode? Actually, to answer that, it's kind of easier if we're looking at this. Right, so it's always cathode minus anode to calculate my standard cell potential. And for my cathode, lead, it was being reduced. But what about for chromium? is I used lead's negative 0.13, and I also used negative 0.73 for chromium. In our reaction, was chromium being reduced? No, it was being oxidized. And if it's being oxidized, these potentials are written for the reduction reaction, right? This is the reduction, chromium plus electrons, adding electrons to chromium. So the cell potential is for the reduction of chromium. And the reason there's a negative in the equation is because when I put that negative in there, it automatically flips the anode potential, because the anode is always going to be oxidized. So you don't have to think about it too closely, but really the reaction that we want is reduction for lead and oxidation for chromium. So we throw in the negative, it reverses the sign, which reverses the direction of the reaction. Okay. So that's like calculating the cell potential. So if an electrode has a negative electrode potential compared to hydrogen, which statement is correct regarding the potential energy of an electron at this electrode? Let's pick an example. Actually, we can use lead. So if I write out, say, take lead, which was the reduction potential, so lead 2 plus 2 electrons gives me a lead solid. That's an E cell or a half cell, negative 0.13. And for hydrogen, its potential is 0. In some ways, you can draw on like Gen Chem stuff, or like, well, I guess this is Gen Chem, but like earlier Gen Chem stuff, right? Like, do metals want to gain or lose electrons? Generally, metals want to lose electrons. So if I if I take this and I rewrite it, right, really the negative cell potential means that that would be a non-spontaneous half reaction compared to hydrogen. So if I rewrite this as lead solid goes to lead 2 plus 2 electrons. Now the E cell is for the oxidation, and it's a positive 0.13 volts, which would be spontaneous. So why is it spontaneous? Why is any reaction spontaneous? At least by one definition. The reaction is spontaneous when lead loses electrons because they have a higher potential energy at the lead compared to hydrogen. So the reaction will be spontaneous in the reverse direction, or losing electrons to something where it's lower potential energy. And that kind of ties back into what I was saying before, where you can think of these negative reduction potentials as the amount of force that that metal or compound wants to get rid of its electrons. If it's more negative, it more strongly wants to get rid of those electrons. So it's at a higher potential energy. So anytime we have when we're comparing anything not to just hydrogen, but comparing two other reactions, if we have a more negative E0, then it tends to lose electrons. If we have a more positive E0, it tends to gain electrons. And notice that it says not positive or negative, but more positive or more negative. So even if I have two positive numbers, the lower one's more negative, the positive, or the higher one is more positive. So if I compared, well, again, the negative 0.13 to the, what was it for that? It was negative 0.73. Right? The negative 0.13 is more positive. The negative 0.73 is more negative. So then if we look at a chart of cell potentials, just based on their positions, we could say the ones that are lower are more negative. They're going to be more likely to lose electrons. The ones that are more positive are going to be more likely to gain electrons. And by pairing those, we can say, is this going to be spontaneous or not? And again, think of this negative as repelling. And so they'll move from the more negative to the more positive. So again, we can do this with actual numbers, but you should also be able to do it without half cell potentials. So here we're just given both reduction potentials. See, these are both gaining electrons. These are reduction potentials. And we want to predict the direction of electron flow for this reaction. I'm just going to do this. Okay. So how do we determine the electron flow? Because we have a picture, we have the cathode and the anode. Huh? I said the negative repels electrons. The one that's more negative repels the electrons. Yeah, so we should see the electrons move from manganese to nickel, which means if this is the more negative, that should be the one that's losing electrons. So that should be the anode. This should be the cathode. So the more negative half cell repels the electrons the strongest. The more negative half cell is the anode. Greater tendency to oxidize. So cathode minus anode means that this is negative 0.23 minus a negative 1.18. This equals E naught cell. .95 volts. So since that's positive, that's going to be the direction that the electrons move. They'll move from manganese. And so actually writing these reactions together, this will be manganese goes 2 plus 2 electrons. So it's actually manganese plus nickel 2 plus goes to nickel plus so reduction is for cathodes. The cathodes are reduced, so that reaction stays in that same direction. For the anode, we have to reverse it. We don't have to do any more balancing here because the number of electrons is 2 for each. 2 gained, 2 lost. So they pair up nicely. Otherwise, we'd have to do half cell redox balancing. All right, so we want to see, is this reaction going to be spontaneous without calculating anything? Nope, almost sneezed, did not. Okay, so these are our half reactions, reduction half reactions in order. You can see hydrogen's at the top. And so first, because we're given this reaction, we need to figure out which of these is being reduced. So is nickel or zinc being reduced? Nickel. Nickel goes from a 2 plus, which is a positive 2 oxidation state, to a 0. So it's gaining electrons. So I'm looking for nickel 2 plus 2 electrons goes to nickel solid. And so this will be that's my reduction. And for the oxidation, we're looking for the opposite of that, or the opposite of the reaction. So for zinc, zinc is being oxidized, which as written is this. But since that's for the oxidation, I'm not going to find that exactly on my table, but I will find the reverse, the reduction of that. And so we can find that here. And to better represent that this is the oxidation instead of the reduction, I'm going to draw an arrow in here that's going to the left. So since it's below nickel on this table, that means it has a greater tendency to be oxidized, which means it would have a more negative cell potential if we knew what the cell potentials were. And as it's being written, it's being oxidized and the nickel's being reduced. So this reaction would be spontaneous. The way you can kind of just memorize this is if you go through on the table and write the arrow to the right and write the arrow to the left, If going from top to bottom, you go right and then left, that'll be spontaneous. So I could pair nickel with any of the reversed reactions below it, and they would all be spontaneous. Anything above it would be non-spontaneous. This one is the other way to think of it is anything lower on this chart has higher potential. Higher potential energy. Anything higher on the chart is lower potential energy. Since we're going to move from high to low, this is spontaneous. Ready. So I'm going to do this with zinc and calcium. Again, we need to figure out which one's being reduced and which one's being oxidized. So what's being reduced? Calcium. So calcium's being reduced. So I'm looking for that, going right to left over here. There's my calcium. And then zinc will be oxidized. I'm looking for zinc. Zinc is here. Right, these are reduction half reactions. But in this whole reaction, it's being oxidized. So we're in left and then right, which means that this is non-spontaneous. Or my oxidation reduction, or my oxidation reaction is higher than my reduction reaction. Because we're taking electrons. Oh no, backwards. This is higher potential energy. This is lower potential energy. They go from the oxidation to the reduction. So lower to higher, non-spontaneous. But the reverse reaction would be spontaneous. So really, if you connected these to a voltmeter, you would read a voltage, but in the opposite direction. I guess depending on how you connect the voltmeter, you'd see a negative voltage. And this is a great one to test this concept. So we got a solution of sodium iodide and sodium bromide. Which oxidizing agent could you use to selectively oxidize iodide, but not bromide? So first thing to do is find iodide and bromide on the chart. And when you get, so this is all the stuff that's above hydrogen. Hydrogen would be below this. When you get above hydrogen, there's a lot of harder to decipher reactions. So iodide and bromide, we've got bromide here. We've got iodide here. I really don't know why the quality of this image is so low. It's that low in the online textbook. But the other part of it looks better. Why? Why, Pearson? Okay, so iodide and bromide, found those there. Now these are being So we want a solution to selectively oxidize one of these. What am I looking for here, right? Selectively oxidize iodide, but not bromide, which means that these are not going to be the reactions going left to right, they're right to left. Because left to right would be reduction, but we want to oxidize. So really these are the reactions that we're concerned with. And some of our choices here are chlorine, Cl2. So chlorine's up here. Hydrogen peroxide. Hydrogen peroxide is hard to find. But it's here. Copper chloride. So I do want to point out, so copper chloride, I've got two different copper reactions. Which one of these represents copper chloride?
Why would it not
There's three.
hydrogen peroxide at the top?
Is there hydrogen peroxide at the top? Oh, there is one at the top. That would make more sense. Actually, we should really talk about why it's not this one. Because this one would also be oxidation. So it can't be this reaction in the middle because then this is oxidation, this is oxidation. So it can't be this one in the middle. Because these are going to be going to the right. So which one of these would be the copper chloride? Probably the middle one, or even the bottom one. A little bit of a trick question. I mean, both of those are Cl2 plus. So starting with Cl2 plus, right, because this is Cl2 plus, 2Cl minus. And for the purposes of this question, it doesn't really matter which one because they're both below. Oh, and the last one, nitric acid. Nitric acid's also hard to find. But really in the nitric acid reaction, it's the nitrate. So I guess which of these would lead to spontaneous reactions in general?
In general?
In general. Like you add this thing, would you see a reaction? So if we add the hydrogen peroxide, would we see a reaction?
Except for the copper chloride.
Hmm. So everything in general would give us a reaction except for the copper chloride, because copper chloride is below our two oxidation reactions. It's got to go right and then left. So this would give me a reaction, but it would react with the bromine or bromide and the iodide. So that wouldn't be selective. The chlorine would also react with both because it's above both. Then nitrate is the only one that's above chlorine but below bromine. Sorry, below, yeah. Above iodide, below bromide. I'm gonna find Alex problems to post for these because they can be a little bit brain twisting with all the positives and the negatives and the lefts and the rights. Practice is the only way.